This conference will now be recorded.
So very good evening, students. We are discussing numerical problems on ray optics. So we have picked up numerical problems from previous year's JEE papers on this topic. So we'll start our discussions. So let us read this problem first. So this problem states that a ray of light traveling in the medium, a ray of light traveling in the direction half whole into I cap plus square root of 3 j cap is incident on a plane mirror. After reflection, it travels along the direction half whole into I cap minus square root of 3 j cap. Angle of incidence is 30 degree, 45 degree, 60 degree, 75 degree. So that is what is the question. I'll just try to make you understand uh, through this diagram. So the question is that a ray of light is traveling in a direction which is shown over here, and it is half I cap plus root 3 by 2 j cap. This is the direction. This is the ray. Incident ray. Now after reflection, the direction becomes half I cap minus square root of 3 by 2 j cap. As you see, this is the incidence, this is the reflection. Okay, this is angle of incidence, this is angle of reflection. Okay, so you have to find out what is the angle of incidence. So look here, in this case, if you see, when the ray comes in this way, okay, so if this is the unit direction, okay, direction, it has it might have component of the vector along this direction, right? So this is along minus j cap somehow, and see, after reflection, actually this becomes like this. See, this becomes again this and this. That means if I take this as positive, then in this direction it may be negative, right? So in this case, if you want to find out angle of incidence, you have to find out angle between this vector, this vector, incident ray vector, this incident ray vector, and the this vector. This is the normal. So normal vector, we can take this as j cap. Okay, we can take this as j cap. Okay, so and you can see here the normal component of this vector is actually changing its direction. Otherwise, the component which is parallel to the plane of the mirror doesn't change its direction. Okay, so if you want to find out the direction between this, then we have to actually find out if we want to find out the angle of incidence, we have to find out the angle between this vector and this vector. Suppose this is j, here it is negative j. Okay, so this is the direction of j in this direction, and this is I cap. Okay, I cap, and this, in this direction, the component has a value magnitude half, and this direction it has square root of 3 by 2, right? So this will give you the angle of incidence if you can find out. Okay, so angle of incidence will be obtained, so tan of angle of incidence, which is this I cap, sorry, I vector, sorry, angle I incidence angle. So this is actually, see, perpendicular by base, that is what we know. So perpendicular is actually here I, the component along the I cap direction. Okay, along the I cap direction. Okay, so that is half divided by root 3 by 2. This is along the vector. Okay, so this has component along this way and this way. This is cos theta component and this is sin theta component. Okay, if I just arbitrarily take this as the reflection vector, okay, if I take this as reflection vector, I'm sorry, incident vector, let us say this is capital I. So this I has component I cos of theta, which is root 3 by 2. Okay, and this is I sin theta, which is actually half. Okay, so that is what I have done here. So that's how we will get, if I say this as theta. Okay, this is actually, I'm sorry, this I should have written I, not theta, I, and so this is cos I cos I, and I sin I. Okay, so from there we'll get tan I. Okay, so if I do the calculation, see, tan I is equal to 1 over root 3. So 1 over root 3 is for actually, see, tan inverse of 1 over root 3. So it will be 30 degree. Okay, so this is 30 degree. So this is very interesting problem, and it is actually is being asked in JEE Advanced 2013. Recently it has been asked again. Anyway, so what we had to do, we had to find out the angle between this vector and the normal. Okay, so we could have done in this way also. We could just take dot product of these two vector, dot product. Okay, so cos theta is equal to dot product of this vector and j by j, and divided by modulus of these two vectors. Okay, so 1 over 4 plus 3 over 4 into 1. So look, from here also we should get the same thing. This actually becomes 1 ultimately. So you get root 3 by 2. Okay, so cos 30 is equal to root 3 by 2, which is nothing but theta is equal to 30 degrees. So this way also you would have done. Okay, so anyway you can do it. Okay, either from the uh, dot product of this vector and j vector in this direction is j. Okay, with that also we could get 30 degree, and in this way also you could do it. Okay, all right, so this was the first problem, and second problem, this is very interesting. We have to understand this problem. A green light is incident from the water air, sorry, incident from water to air water interface. I mean, see, this is coming from water to air. Okay, this is suppose air, and this is going like this. Okay, so this is the water, this is air, so ray should be straight line. I'm sorry, I'm not able to draw a straight line like at this moment. Anyway, so just to understand, this is the water and this is the interface. water air interface. Okay, and see this light, a green light is incident from the water to the air. I'm sorry, green light from water to air water interface at an angle, at critical angle. This angle is critical angle. Okay, this angle is critical angle theta. Select the correct statement. Okay, we have to find out which one of these statements, four statements, which one is the correct one out of these four. So we know two things. See, we know if theta is the critical angle, so we know the condition for TIR, total internal reflection. Total internal reflection will happen only when the angle of incidence will be greater than the critical angle. That means this must be greater or equals to 1 over refractive index n. Okay, refractive index n. So this is the condition for TIR. Okay, we have few more things to understand here. Let us first read the options one by one, and then we'll try to analyze. So the statements are: first statement, the entire spectrum of visible light will come out of water at an angle 90 degree to the normal. So the entire visible light will come out of the water at an angle 90 degree to the normal. That means it is said that the entire visible light will be seen like this. It will come out like this. Okay. After refraction, it will actually graze the interface. This is what is said in the first option. See, in this case, you need to look two things. One is the condition for condition for total internal reflection, and at the same time, see, you have visible light, you have VGOs, that means different colors. Okay, so all the way to violet to red. Okay, VGO up to red. So entire spectrum means violet, then you will have green, then you will have yellow, etc. So in between there will be some five. Okay, so there are seven colors total. Okay, in the visible light. But see, when there is refraction happening from water to air, we need to see whether any of the color is satisfying the condition of this TIR. If any color satisfies the condition of TIR, then it will actually remain in the water medium, that will not come out of the air. Okay, but if color is not satisfying the condition of this TIR, then that will actually come out of the water, that will go to the air. So in this case, you look, the entire spectrum of visible light will come out of the water at an angle 90 degree. This could not be true, because we don't know what is happening for each color. Let us see now. See, we know c is the speed of light in air. So this c is the speed of light. That means the speed of all the colors are same. Okay, here we know nu frequency into lambda air. Okay, generally during refraction or reflection, frequency doesn't change. That's what we know for a particular light, for a particular color, but different colors have different frequencies, that we know. Okay, now what is the speed of that particular color? A particular color has speed in the air different, so in the medium, and different in the air. It will be c, and that will be same for all the colors. Here now Vm will be nu into lambda m. So this is, see now refractive index is given by, this is refractive index is given by V by, sorry, C by Vm. V, that means the speed of any color in air divided by speed of that particular color in the medium. So if we just take the ratio, what we get is lambda air by lambda medium. Okay, that means, see, the refractive index, this refractive index is dependent on the color, because see, refractive index is, anyway, this is common for all, so refractive index is inversely proportional to lambda. That is what we can understand from this thing. So what does this mean? It means, suppose I have green light. Now as you go towards red, lambda will be increasing, right? If I have some light who says wavelength greater than this red light, sorry, greater than the green light, then see refractive index will be low. Okay, smaller, refractive index will be smaller according to this relation. If that happens, then see theta c will be actually greater than theta, sorry, theta will be greater than theta c. That means angle of incidence for, I'm sorry, that in that case, okay, so theta c, from this relation we can understand theta c for lesser wavelength, sorry, greater wavelength, theta will be actually greater than, sorry, theta c will be greater than the angle of incidence in that case. Okay, I'll just clear this out again. Let us go to the next page. So we have now condition for TIR, that is sine theta, suppose this is the angle of incidence, critical angle, this is greater or equal to 1 by n, refractive index. Now we have a relation between refractive index and the wavelength as this. Okay, that means if some light, some color has wavelength greater than the green light, or there are whole lights, all the colors, right? The light which has greater wavelength than the green light, that will have actually lesser refractive index. Okay, suppose this is green, lesser than green. Okay, any, I'm sorry, lesser than green. Okay, lesser than green. In that case, you look, if I just put it here, then if the theta is the angle of incidence, sorry, critical angle of incidence for green, then since this is less, then it will be more. Then theta c for the other color will be greater than theta, right? So those lights will not be able to meet TIR. Okay, so they will be obviously passing through. I hope it is understandable. I'm saying that if I have different colors, so different wavelength, lambda green, okay, then lambda blue, I have different colors, lambda red, all these I have. Blue obviously will be less than green, and red will be greater than green. So if some light or some color has greater wavelength than green, then for that the angle of critical angle of incidence for TIR will be greater than theta. Okay, how? Because refractive index, see, it is actually inversely, sine theta is greater or equals to 1 over refractive index. If the refractive index is small, okay, small, then this will be more. Then some of the light or some of the colors will not be able to meet the TIR condition, so they will not graze the interface, or neither it will come to the water, it will actually pass through the air. So that's why this is not true. Entire spectrum of the visible light will not come out at an angle 90 degree to the normal. It is not true. Okay, I'm sorry, this is not true, because some of the light will not satisfy the condition of critical angle. Okay, some of the colors. Now the visible light, the spectrum of visible light whose frequency is less than that of the green light will come out to the air medium. Now we'll just think about it. So frequency of light which has lesser frequency, suppose red. Okay, this is frequency of red is lesser than green. Okay, lesser than green, this is the frequency. Okay, that means individual light has greater frequency. That means, you know, this has lesser wavelength, green has lesser wavelength than red. So in this case, what will happen? What will happen? So see, if lambda is more, then this is less. This is less. So if this is less, that is what I have discussed already. If this is less, then this sine theta, this theta will be actually more. If lambda is more, then refractive index is less, then angle of critical angle of incidence will be more than the angle which is given theta for green. Okay, so if that happens, if critical angle is greater than theta c, sorry, theta, then it will, see, the question, the answer was entire spectrum whose frequency is less than that of the green light, that of the green light will come out to the air medium. So it seems which has greater, okay, let us go with this. If the lambda is more, suppose this is red, lambda is more means frequency is less. So lambda is more means frequency is less. So this is less now. So this is more. Okay. So this factor is more. That means if at this particular angle of incidence, okay, so it is not possible to meet the TIR. Okay. Now let us see when the frequency is some blue has greater frequency than green. Okay, blue and green, let us see. So this has lesser wavelength than green. If we consider this lesser wavelength, then refractive index is more, then angle of critical angle of incidence will be less than, in this case critical theta c must be less than theta. That means, you know, the color which has wavelength less than green or frequency more than green will be able to meet the condition of TIR with this angle of incidence theta. So the frequency which has frequency more, they will actually suffer total internal reflection. So the next option was that. So the spectrum of visible light whose frequency is more, so this will actually come out of the air. This is not true. So it will not come out of the air, come out to the air. This will remain. So actually this satisfies, because this satisfies TIR. Okay, but this will not satisfy TIR. So the colors or which are having frequency less than that of the green, they will actually refract to the air. So this will come out of the air. Now look, see the last option. So third option is not correct. Entire spectrum of visible light will come out out of the water at various angles to the normal. This is also not true. Okay, I think I will just summarize what we have done here. See, we know the TIR condition TIR with this theta critical angle with the incidence we have been given here. This is the condition of TIR, and we know refractive index is inversely proportional to the lambda of the light. Okay, so when it refracts at an angle theta from water to air, so what happens if this theta is the critical angle for this particular green color, for green color, then this angle theta will not be the critical angle for all the colors. This is the main point. Okay, this will not be the same color. See, critical angle may be greater than theta for some colors, or it may be less than theta for some colors. Okay, less than theta for some colors. So the light or colors for which the critical angle is greater than theta, they will not satisfy TIR. Okay, they will not satisfy TIR. So they will actually pass through and they will come out to the air medium. But the colors for which the critical angle is less than theta, they will actually satisfy TIR. They will actually go to the water itself by TIR. So in this case, we have seen, see, if someone has wavelength, say I have G, wavelength G, green. If some light has frequency less than green, that means it has wavelength greater than the green. If wavelength is greater, then see, it implies that the refractive index of that particular color will be less than the green light. So in that case, from this TIR condition, we can see the angle of theta c must be greater than theta. Okay, must be greater than theta. So with this we can understand that the spectrum of visible light whose frequency is less than that of the green light, they will actually come out to the air medium. Okay, all right, we'll move on to the next question. So this is again very interesting problem, and this is from prism and critical angle of minimum angle of deviation, that particular portion. See, the question says, in an experiment for determining the refractive index of the glass of a prism, refractive index of the glass of a prism by I delta curve. You know, I delta curve we have already discussed in the previous day. Sorry, this is delta and this is I. It 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 turns out to be like this. Okay, so this is the minimum delta minimum. Okay, and for each other than this minimum, for each delta there will be equal angle of incidence and equal angle of emergence. Okay, either side of the prism you can use for the experiment. So that is the fundamental idea. Okay, so here the minimum deviation, and in this case actually R1 will be equal to R2. So those things we have already discussed. The question is, from this plot we can find out the minimum angle of incidence, minimum angle of deviation, or angle of deviation, angle of corresponding angle of incidence we can find out, and that angle of emergence we can find out. In that case, which of the following is closest to the maximum possible value of refractive index? So the question is, in an experiment for determining the refractive index of a glass of a prism by I delta plot, it was found that a ray incident, so for the ray, angle of incidence is given as 35, okay, and surface angle of deviation, that is given as 40 degree, okay, and that emerges at an angle 79 degree. In that case, which of the following is closest to the maximum possible value of refractive index? Okay, so we know there is a relation between delta, angle of incidence, angle of emergence, and this is angle of prism. Okay, angle of prism. I hope there is some more information which is missing. Let me just, angle of prism has to be given. Let me check whether I have typed it wrongly. Okay, this is the thing. We have to go with this. Let us see whether we can find out what is A. Oh, I'm sorry. From here itself we can find out, since I, delta, and E are known. So from here A can be found out. So A will be I plus E minus delta. So I is 35 degree, and then E is 79 degree minus 40. So this will give you, see, if we take this, so this is minus 5. So minus 5 means it is 74 degree A. So angle of incidence, sorry, angle of prism we have found out, then how much? 74 degrees. So we can write it somewhere, and I'll erase this relation. Okay, this relation. So angle of prism we have found out 74 degree. Now look, if delta is minimum, see, if this is the delta, and for that we have got, see, angle of incidence and angle of emergence difference. So some different angle we have got. So at the minimum angle of deviation, both this angle of incidence and angle of emergence will be having the same value. Okay, and so this angle of deviation, minimum angle of deviation, must be less than 40. Okay, now we know mu is less than, if this is this we have, if this if we just go with this 40 degree as minimum angle of deviation, so with this we can write mu is less than sine of a plus delta, you know that, sine I by sine I, this is I, sine a plus delta by 2 at minimum angle of deviation, at minimum angle of deviation. Okay, and this is sine a by 2. Okay, sine r, this one, because r1 plus r2 is equal to r is equal to a. So sine r at minimum angle of deviation, this is the condition. Since this is minimum angle of deviation is less than 40, so this is what we can write from here. So this is then, see, a is 74 plus this is 40 divided by 2, and this is sine of 37. Okay, so if you just calculate this, this is actually, this will give you nearly this. value, okay, nearly 1.51. So mu for maximum possible value of refractive index, the maximum possible value can be this one, okay. So here this is closest to 1.5, okay. So this is how we have to solve this problem. Now we'll go to the next problem. So this problem is also again interesting problem, okay. So let us see, a parallel beam of light is incident. A parallel beam of light is incident from air at an angle alpha on the side PQ of a right angle triangular prism of refractive index n is equal to, this is root 2, I'm sorry, this is root 2, n is equal to root 2, as you see here. Light undergoes total internal reflection in the prism at the face PR, at this phase. That means here the critical, it is actually satisfying TIR at the face PR when alpha has minimum value of 45 degree. This is degree. When 45 degree, okay, alpha has minimum value 45 degree, then the angle of theta, that means the angle of prism is 15 degree, 22.5 degree, 30 degree, 45 degree. So this is actually JEE main, not advanced. Main 2016. Okay. So look here, you have been given alpha. If you choose this to be minimum, alpha minimum is 45 degree. If we go with that, then there will be there will be total internal reflection from this PR. Okay. So the angle of theta of the prism is, so look at this interface, sub PQ interface. At PQ interface, we can apply Snell's law. So we can write 1 sine alpha, and we don't know what is the angle of refraction, let us say. So this is root 2 into sine of beta, angle of refraction, okay. All right, or let us say this is R, angle of refraction, let us say that to be R1, okay. So what is R1? If I take this to be 45 degree, alpha to be 45 degree, then see sine R1 is equal to 1 by root 2 into sine 45 degree. If I just choose this value of alpha, so then it will be half. So half means what? Sine 30 degree will be half, right? So R1 is 30 degree. So see here, then it will be refracted here like this. This is the normal over here. So this is 30 degree we have got. This is R1 and say this is R2. Okay. Now if that is the case, then on the other side, what we can write? On the other side, we can write here. See, this is let us say root sine R2 is equal to 1 sine 90 degree, right? it will be 90 degree here, because it is just satisfying the total internal reflection. I'm just taking the just satisfying condition so that this becomes critical angle. Okay, so that means r2 is becoming 1 by root 2. So sine r2 means this 1 by root 2. So this will be, so theta c at this particular surface, theta c is actually 45 degree. Okay, if that is the case, then what is the angle of so this r2 is 45 degree. Okay, r2 is 45 degree. So what are the information we have got? Now look, we'll just take help of this figure. Okay, we'll just erase this and I'll write down the information here briefly. If we take the minimum value of this alpha to be 45 degree, so then we have got r1 to be 30 degree and r2 to be 45 degree. So we have to now consider, see, let us say this point to be some m. Okay, some m point. So I have got a triangle, right? I have got a triangle PM. Look, PM, and this is suppose N. So I have got a triangle PMN. So from here, see, if I just add up all the angles, so uh, this angle, this is 90 degree plus 30, right? So R1 plus 90 degree, and this angle is actually, this is 90 degree total. So this is again 90 degree minus R2. This is equal to 180 degree, right? So look here, this 80, 180, this 180 will cancel each other. So we'll get R2 minus R1 as theta. Okay, R2 minus R1 as theta. So what is then theta? Theta is the angle of prism. This is R2 means 45 degree minus this is 30 degree. So we get 15 degree. Okay, I hope you have understood this. I am not repeating it. Okay, so I just brief out then what we have done. We have just first applied Snell's law at this particular PQ interface. Okay, as we know, the angle of uh, angle of sorry refractive index we know, and alpha we have just chosen to be 45 degree as given here. Then we will get actually what is R1. Now we know it is happening total internal reflection, so I'm just taking the critical condition. So at critical condition, here I can apply the Snell's law, which is here. Okay, this is as critical angle. Okay, so R2 is equal to theta c is equal to 45 degree. So if I get this as 45 degree, so it this is total is 90 degree, so this will also be 45 degree. Okay, now we have 45 degree, and this is 90 plus 31 degree, sorry 120 degree. So what will be this? Okay, so we have got 45 plus 120. Okay, that means we have got 165 from these two angles, so theta will be 15 degree. Okay, this is how we can solve the problem. Okay, we'll take up the last problem for today. I have to write down this problem. Let us write down it. A ray, I have just given the figure here. A ray of light AO in vacuum is incident. In vacuum is incident on a glass slab on a glass slab at angle 60 degree and refracted at refracted at angle 30 degree, as you see from the figure itself, along OB as shown in the figure. Okay, the optical path length of the light ray, the optical path length of the ray from A to B, from A to B, A to B, sorry, A to capital B, A to capital B is, options are given. First option is 2 root 3 by A plus B. Second option, sorry, this is 2B. Second option is 2A plus 2B by 3. Third option is 2A plus 2B. And fourth option is 2A plus 2B by root 3. Okay, so we have to find out what is the optical path length from A to B. So it is actually optical path length means, see, this is in air, this is air, and this is glass, right? So optical path length, this AO will be AO only. So optical path length will be path length from A to B will be AO, this much length, plus mu is the refractive index into OB. So this will be actually the optical path length. Now we have to actually find out what is OB, what is AO. Okay, see from the figure AO can be written as, so this is actually, see, if I just write down here, if I write here, it is, so this is also A, right? This is also A. Okay, so this is, see, if I say this is a right angle triangle, then you know this will be hypotenuse. So A by AO will be cos of 60 degree, right? That means AO will be A by cos of 60 degree, right? So this will be cos of 60 degree means half. This will be 2A. A will be actually 2A. A will be 2A. And what is OB? OB, this is again, you look, this much is B. This much is B. This is 30 degree. So OB, again, OB will be OB will be, see, sine, this is also cos theta. Okay, so it is B by cos of 30, cos of 30, cos of 30. So cos of 30 will be how much? This will be actually, so root 3 by 2, so 2b by root 3. We'll just write this informations in the next page. So path length will be, so let us say path length is some L. This is AO plus mu into OB. So AO we have obtained, mu into, then it is 2b by root 3 is obtained. Now for glass it is already given, but still we can write it. What is the refractive index here? See, 1 sine of 60 degree is equal to some n sine 30 degree. So from here what we get, n is equal to, so 60 degree means sine 60 degree means root 3 by 2, and divided by sine 30 means half, so that half will go to numerator, so this will be root 3. So refractive index of the glass is root 3, we know that for this particular case. Okay, so root 3 from the figure. Okay, so root 3 into this, into 2b by root 3, so root 3 cancels up, so we get 2a plus 2b, and let us see whether we have this kind of options. Okay, so this option C will be the correct answer for this question. Okay, so this question was being asked actually in JEE mains 2019. So it was main 2019 problem. Okay, so with this we'll stop it here for today. We'll pick up many more problems on this particular chapter, because this is a chapter which seems to be the toughest part of the optics. So ray optics seems to be much more tough than the wave optics part. So we'll pick up more questions on this ray optics part, okay, in the next classes. So thank you for your patience. Bye for today.